Well, hello and welcome to our latest webinar and the first in our sustainability series, where we're going to be looking at the prospects for disruptive propulsion. Now, the past 12 months have been terrible for aviation, but they've also seen a flurry of initiatives to develop alternative power sources for aviation, from electric batteries to hydrogen, as the industry and governments look to a world beyond carbon dependence. So how realistic is it that one of these alternative power sources can lead to the sort of technological breakthrough needed to change the way aircraft have been powered for more than a century? Some believe that we're only years away from such a revolution. Others that green evolution in carbon-based propulsion is the most likely and the most cost-effective way forward. So joining me today are four experts from industry who have very different views, I suspect, on what is possible. But before I introduce them, a reminder that we're live for the next hour, and there'll be an opportunity for you to pose questions to our panelists. So please use the Q&A icon at the bottom of your Zoom screen, and we'll try and get through as many of these as possible. From our sponsor today, Pratt Whitney, I'm delighted to welcome Michael Winter, a Senior Fellow for Advanced Technology. Michael is responsible for identifying and prioritizing the technologies of tomorrow and leading on intellectual property, technology licensing, and partnership programs. Matthew Thomas is the lead architect, effectively the chief engineer, for Airbus's ZeroE initiative to develop a zero-emission concept aircraft. He's been with the European manufacturer for 13 years, and prior to this role, worked in Airbus's Future Project Office, where he led on the hybrid propulsion studies. From GKN, we're joined by Chief Technology Officer Russ Dunn, who, among other things, is responsible for sustainability at the UK headquartered company. GKN, as you might have read, has just launched the development of a hydrogen fuel cell powertrain, backed by a grant from the UK's Aerospace Technology Institute, which it thinks could enter service in 2026. And finally, from the world of startups, Neil Cloughley, Managing Director of Faraday Aerospace, believes that hybrid electric technology is the answer to challenges in urban and regional air mobility. The company's bioelectric hybrid aircraft is one of many possible disruptors in this sector. He believes Faraday can have 300 examples in service by 2030. So, Michael, if I can start with you, can disruption come from established players in the propulsion market, such as Pratt Whitney, who, as you might say, might have a vested interest in maintaining current technology as long as possible?
A great question, Murdo. And when you think about it, for 95 years, Pratt Whitney has really embraced disruptive innovation and brought it into the market, from the WASP engine to the twin spool gas turbine, and most recently with the geared turbofan. And we're really well positioned with the next generation of technologies as well for sustainable aviation. If you think about it, in order to meet the industry goal for 2050, most of that's going to happen in the long-range missions. 80% of fuel burn happens in more than 1,500 kilometer missions. And so when you look, starting with the traditional gas turbine engine, with propulsive efficiency, we have tremendous room to grow, and we're working on the technologies that go deeper into the design space of the geared turbofan. Relative to thermal efficiency in the core of the engine, with new manufacturing technologies and investments we're making in that, and new material systems, again, there's huge opportunity to grow. But on top of that, we've also, over the years, worked with fuel cells, we've worked with hydrogen, and we've worked with electrification. For electrification, we're currently working on a turboprop demonstrator, which is essentially a 50% hybrid electric. We're also bringing those same motors, drives, and generators to a geared turbofan, which would be a hybrid electric instantiation for a single aisle application. And we're working on that in partnership with NASA. With synthetic aviation fuels, that's a very easy to get from where we are today with 7 fuels certified up to 50% blends to the 100% level. In fact, we've run engines for more than a decade on 100% synthetic or sustainable aviation fuels. And even with hydrogen, our engines are agnostic. We'll burn anything. And so back in the 1950s, we actually developed and ran engines that ran on hydrogen. Not only just hydrogen burning in the gas phase, but even starting with liquid so it would fit on the aircraft with expander cycles. We're even working on ammonia, where you replace essentially the carbon in the fuel with nitrogen. And we're doing that in concert with our research center. So we're actively working on all these technologies so that as a company, we'll be well positioned to take advantage of that.
Okay, thank you, Michael. Matthew, tell us about Airbus's ZeroE project. Is this just a way of the world's biggest airliner manufacturer ticking the sustainability box, or is zero emission travel a realistic prospect in our lifetimes?
Yeah, no, in fact, the climate change is extremely important for Airbus and for all big companies, even small companies, even startups. So that's really something we all work on. Maybe the first thing is to remind a little bit the context. And it starts obviously with the decarbonization targets the aviation has set itself. So I remind it's minus 50% by 2050 compared to 2005 levels. So this is already an extremely ambitious CO2 reduction target. So we know the different solutions to go in this direction to solve this problem. It's a question of aircraft efficiency. So for example, improving the gas turbines, as Michael said. There's a question of operation, improving the aircraft operations, including the air traffic management. And there's also the massive use of sustainable fuel, either biofuel or synthetic fuel. So these are all the enablers to significantly reduce the CO2 emissions of the aircraft. But it's only a part of the problem, because the real challenge in front of us is not the CO2 reduction, it's the climate impact. So it's not only CO2, it's CO2 plus NOx plus contrails. And it's having this in mind that we revealed to the world that we're working since already several years on ZeroE concepts. And the solution we see for all this is the use of hydrogen as a fuel, since it's the most powerful enablers to significantly reduce the aircraft emissions, not only CO2, but also NOx and contrails.
Okay, thank you, Matthew. Well, Russ, as Matthew just was talking about there, we've been hearing a lot about the potential of hydrogen power. It would need not just a breakthrough in the way aircraft and engines are put together, but a sea change in terms of support infrastructure. I mean, what sort of timescales and the size of challenge are we talking about?
I mean, first of all, I think the aerospace industry is a hugely diverse industry. You know, there are many different categories of market and different needs at an aircraft and platform level. And in order to transform the sustainability of aviation, you're going to need to tackle all of those. No one single technology, no one single company is going to be able to achieve what we as a group can and should achieve. I personally believe, and I think GK Aerospace believe, that hydrogen is a key one of those ingredients. As Michael said, you know, clearly that can be from combustion and can also be through using a fuel cell to generate electricity on the aircraft. From our point of view, clearly, you know, we have made a decision to accelerate and to develop our capability in this space. And the reality is, I don't think any of us know just how far that technology will enable you know, air traffic to progress and how quickly. We have an aspiration over this 5-year period of our program to get to a position where flight is absolutely possible and demonstrated using cryogenically cooled hydrogen. However, we've got an awful long way to go to get to the point where we can demonstrate that, you know, anyone who's certified an aircraft before will know just how much work goes into it. And we'll probably find more hurdles along the way than we even can envisage at this stage. So, you know, however, having said all of that, you know, it is we have a fantastic opportunity and also responsibility to take some of these, you know, bold moves. And I think that's where we in GK Aerospace want to position ourselves, want to inspire the industry, want to inspire the fantastic customers we work with, and work with them to take these important steps.
Great, thanks. And Neil, if I can move to you, the problem with electric technology is not that it can't work when it comes to powering aircraft. I think that's been proven, but it's a question of whether we can scale up the platform to carry large numbers of passengers. And I guess it's also a question of business scale. Why do you think this is something that startups like Faraday can do better maybe than some of the bigger companies?
I think when you look at innovation throughout aviation history, you look at how small teams have been able to produce phenomenal things. Look at what the Skunk Works team created out in America with things like the SR-71. Small teams are enabled to work very quickly, very nimbly. When we first started working in this sector some 6 years ago now, we founded Faraday in 2014, so we've been doing this a long time now. There were differing opinions as to what the future was going to be. Some people were thinking we were going to have fully electric aircraft by 2020. Some people were thinking we're going to be doing all sorts of fanciful things. The reality is we have to do things in incremental stages. So from our perspective, we were always going to develop an aircraft that was agnostic of the end power solution. So we started with the idea that hybrid would have to be the first point of call. And the reason for that was very simple. If you can take that power generation bit out of the equation right now as an obstacle, i.e. if you can use the existing technologies that are type certified approved, run them on a sustainable aviation fuel or a fuel yet to be really developed further, then you've got an instant deployment capability at places throughout the world. What we're trying to solve here is the fact that in the year 2021, we are still landlocked to many intercity routes. The Wright brothers flew over 100 years ago, and we're still locked into these land-based routes. So what we've got to be able to do now is begin that transition where the much underutilized airspace becomes a genuine regional and larger scale mobility opportunity for a lot of people, in which case, let's start with stuff that's proven and capable. Let's put a big dent into the emissions market by using sustainable aviation fuel, etc. But as we've done with the BHAR, what we're then doing is we've basically built a net zero airplane for the future. This aircraft will be net zero in the future. Now, whether that's going to be battery pack or fuel cell or ammonia cell, whatever that's going to be that replaces the turbine, that's what we'll put into this aircraft. So it's got longevity, but in the short term, we've partnered with Honeywell and we're using effectively the APU and their new generator that sits in the tail of the Airbus A350, one of the most modern aircraft in the commercial fleet. So it's a sensible step in the first run. And then what comes down the line, who knows? It's going to be down to the development programs of the guys developing these technologies.
Excellent. Now we're getting some questions coming in. I'm going to turn to them in just a minute, but just a quick question for whoever wants to come in on this on the panel. We've obviously seen governments step in to lead this initiative in many ways. But does anyone have a view on what the role of states are, what the role of government is, and what the role of private sector is? We've just seen United Airlines giving Archer a $1 billion commitment for its eVTOL aircraft, and former Boeing CEO Dennis Muilenburg has just set up a new company to invest in, among other things, alternative propulsion. Is the market in a position to back some of these things yet, or does governments really have to be the catalyst? Russ, do you want to come in on that first?
Yeah, so I guess my view of this is, the industry that we have is very much driven by market measures. We have developed products which meet a market need, which meet achievable sort of economic and financial goals. For me, the thing that governments around the world can do is enable us as an industry to get beyond that sort of first phase where things are extremely expensive, to get over that hurdle to a position where the market drives sustainability as the things that we want to achieve through sustainability become the right financial solution. As with all technologies, that initial period takes an awful lot of investment. the support to get over that hurdle, so it then becomes, a more sustainable, self-sustaining market in some of those areas. That's where I think governments around the world, that's the support I think we need.
Does anyone else want to come in on that question?
I do.
Michael?
So when you think about the infrastructure, let's start big. Let's think about the infrastructure involved. The commercial fleet burned just shy of 100 billion gallons of fuel in 2019, right? If you look at that from an electric generation scale, it's a little more than 600 gigawatts, right? Put it in perspective, the world's largest nuclear plant, which has 14 reactors in Japan, is a 7 gigawatt, right? So you need about 100 of those, right? And if you go through the numbers, that's either for electric propulsion, or if you want to make electrofuels, for example, to produce the hydrogen, it's of order 700 gigawatts, right? That's going to be more than $3.5 trillion investment in the time frame. So at the very largest scale, the infrastructure to have the hydrogen, or even if it's power to liquid fuels, to have that available on the flight line is going to take a significant investment. As you go and you look at the individual technologies, all the technologies that we introduce will be as safe or safer than the aircraft that are flying today. That is not a compromise any of us are willing to make. And so in order to accomplish that, those technologies have to be learned out. And here we are coming off of the pandemic where our industry is under duress, right? So the role of public-private partnerships is going to be really important to invest in these technologies. Now, the good news is when you think about the tax incentives or how carbon offsets and market-based measures might come to play, taking some of that money and reinvesting in these technologies from a public-private partnership standpoint would be absolutely phenomenal to leapfrog the industry forward.
Thank you, Michael. Neil?
Yeah, I mean, I'd just like to follow on that sort of thought basis. What we're seeing at the moment with the announcement we saw yesterday and both the development certainly we've seen over the last 6 years, the aerospace industry is about to go through a massive change. The ways of doing things for the last 10, 20, 30 years, forget it, they're done. The world is moving at a different pace now. Silicon Valley, for all of its merits and negatives or whatever it may be, they are driving a whole new way of doing things, which basically means throw an awful lot of capital at something and run really fast. That doesn't mean sitting and doing white papers. It doesn't mean contemplating things and doing little small things. It means throw a huge amount of money at some projects. We've seen yesterday's announcement by Archer, a 3.8 billion valuation on a company that has not even produced yet in physical form an aircraft. And they've managed to secure a 1 billion order with a major airline. Now, no taking anything away from these guys. That is a phenomenal achievement, absolutely phenomenal. But what it also does is give you a very sanguine look at what is going to change now. Because if you look at the general aviation market, let's go back to 2019, 2020 is going to be a wash. But that was effectively 3,500 total assets deployed in general aviation in 2019, new assets. Now, of which we're saying Archer is going to then place 200 new aircraft into that market on that order with United. Robinson Helicopters delivered, I think, 196 helicopters in total in 2019. So they're coming in and instantly competing at that end of the market. I mean, let's face it, eVTOLs are not going to compete with twin turbine helicopters in the first instance. We're talking small helicopters. So if you pulled any executive out of Robinson Helicopters today and said, we're going to throw enough capital at you to give you a 3.8 billion valuation, there'd be some very big smiles and faces in that office. They'd think it's Christmas. But what that's going to do, it's now going to actually justify the future market, which is with COVID. And whilst the aircraft business has taken an enormous beating in the last 12 months, what we're actually seeing is a huge opportunity now for us to completely reset, go at sustainability from an aerospace perspective, and actually start making some fundamental changes. Now, a lot of the smaller companies have got the ability to do that far more nimbly, supported by the big primes. And when the big primes step in and go, you know what, we know what we're good at. We know we're great at certification. We know we're great at rollout of products at grand scale. But doing the early stuff, I remember one of the guys talking to me about how they use 60 engineers at Airbus to design a winglet. You're not going to do that in some of these startup companies. You're going to be working with a team of 5 to 10, and they're just going to go at it morning, noon, and night. So it's a changing time in our industry. And I think that means that government and both regional bodies and industry and investors, et cetera, are going to now start coming to what is going to be known as a new normal. It's an exciting period.
Exciting indeed. Matthew, COVID has obviously taken over everything and changed everything in the last 12 months. But just before that, we were in a climate crisis, and aviation was being portrayed as the villain. We had flight shaming. We had campaigns against flying because it was dangerous, damaging to the environment. What role can aerospace play now in that, as Neil referred to, that reset, that using disruptive propulsion to change the whole image of aviation?
Yeah, even if my feeling is that it's a little bit unfair, because the aviation emissions is only 2 or 3% of the global emissions, so it's a little bit unfair to point out like this aviation. But well, that's how it is. Now, let's say we have to take our part of the challenge, of the big challenge, which is to reach climate neutrality. So you mentioned this previously. Let's say the governments, the states already they are already defining very ambitious targets. We speak about climate neutrality by 2050. It's in Europe. UK already stated this before. Japan did the same. So we have to go in this direction. And the aviation industry, we said, well, what can we do? We have to try, first of all. And that's what we're doing in Airbus. We say, well, let's explore the different aircraft design, the different concepts. Let's try to find the right fuel, the right propulsion system, the right aircraft platforms, so as to go toward these directions, and then we'll see. So that's what we've started to do since several years in Airbus. 3 years, we started to explore, and we'll define what's the best option. Is it using hydrogen with fuel cell? Is it using hydrogen with gas turbines? Is it a mix of both? Is it first of all to introduce a regional aircraft or a bigger one? It's all these debates, all these explorations that we're running, so as to try to define the best solution. And the idea is to select this by 2025, so as to have first zero emission aircraft on the market near 2035. That's the target we have in mind.
Okay, thank you. I'm going to come on to some questions from the audience now. Again, these are some of the issues that we've been covering already, but we've got a question from, and forgive my pronunciation, Catalan Fortash. My question for the panel is I'll just paraphrase a little bit here, but what is going to be the economic drivers for disruptive propulsion? Is it going to be a societal push for lower emissions? Is it going to be, and this kind of covers what we've just been talking about, push from government, or is it going to be pure economic logic that these are just going to be, it's going to make aviation cheaper, it's going to make fuel cheaper? Who wants to come in on that? Michael?
So when you think about the future scenarios, we've talked about a couple different possibilities. Could be hydrogen, could be sustainable aviation fuel, could be electrification. It's likely to be some superposition of all of those. And each of those, there's a series of triggers, if you will, that say that these scenarios are beginning to manifest themselves. And those triggers manifest in terms of either supply side, meaning there's a new technology, a technology breakthrough, demand side, such as you just talked about in terms of the importance of climate change and the perception of society of what it means to fly, right? Or it could be government mandate or government fiat, if you will. It could be in terms of taxation that equalizes the cost, either taxation or credits that equalizes the cost of sustainable aviation fuel to jet fuel. It could be in investments by governments in the infrastructure that brings hydrogen to the flight line. And so those are the key things to keep an eye on. It's really those three drivers that will bring it forth from an economic standpoint.
Okay, I'm going to bring in Neil next and then Russ.
Yeah, I mean, I think from when we started this program, the whole objective was to solve the three fundamentals. And the three fundamental problems why we're not flying regionally is cost of operations, noise, and emissions. You've got to solve those three problems. If you don't, forget it. If you don't solve those problems, you're not going to increase what we're doing at the moment. So, for example, if we could offer the ability for people to go from London to Manchester in 45 minutes to an hour, and it costs them £25 each way, I know for sure I will fill every single seat, every single 18 seat on that airplane will fly fully booked, because that's what people want. They want affordable transport. If they can do that with some green credential as well, even better. But ultimately, what we're trying to do here is we're trying to improve people's lives. We're trying to give them faster connections to intercities. We're giving them the greater choice of where they can live and then still commute to the jobs that pay the higher salaries. And then we're looking at a whole wider societal benefit globally. I mean, we can, in the West, we get very caught up with focus on how we talk about our intercities. Think of the number of journeys from humanitarian aid perspective of basic ingredients like grain and food and water in places like Africa and developing nations that currently get caught up in land transit. Now, if we can start looking at doing things with aircraft cost effectively, where you've got opportunities, and that's why, again, the BHAR is a utility design, because you've got to be able to serve different markets. And it's a great way to introduce some of these technologies and introduce how we can bring real benefit. If you look at the likes of hydrogen, etc., the ability to store excess off the offshore grid, or the ability to turn major airports and all the infrastructure and the ground trucks to hydrogen vehicles, electric vehicles, that is just so obvious as to why you would do that. But are we actually going to spend trillions and trillions of dollars putting infrastructure into airfields that don't even get served by existing assets today? No, of course not. So Michael is absolutely right. This is going to be a blend and a mix of a whole range of technologies over the next 10, 20 years. And there are going to be some huge opportunities to be taken advantage of in that.
Russ, you wanted to come in on that?
Yeah, so I mean, some of what I was going to say has been covered by Neil, but I mean, ultimately, you know, what our customers, the end customers, are looking for. There will be some who absolutely will choose a particular flight, a particular vehicle, a particular route because it is the most environmentally friendly. But we probably also need to accept that the vast majority are simply looking for either convenience or price. So we need to be able to give the customers what they're looking for. Some of that convenience will come through some of the things Neil's talked about, you know, offering routes which are much more direct between locations that have not been serviced before. But we also have a significant amount of that price piece. And yeah, how do we ensure that there is a value to sustainability? And that value is enabled either through new technologies or through other market-based measures that allows, you know, people to make that choice in a price competitive sort of landscape. So I think, you know, adding probably sort to Neil and what Michael already said.
Excellent, thank you. Another very interesting question here from the audience, and it's I'm going to read it all because the audience member puts it very well. Hydrogen and electric power have great potential but face huge challenges. And what we really need to do is work hard on reducing emissions now and looking at things like sustainable alternative fuel, which is on the verge of becoming a viable option for commercial operations. This person wants to know whether we're focusing maybe too much on the medium to long term in terms of disruptive technology, when we should be focusing more on the short term achievable things, such as sustainable aviation fuel and such as, I guess, you know, iterations to current technology to make, you know, current engines more efficient. Does anyone want to come in on that one? Let's go to Matthew first, then Michael, then Russ.
I think it's a very good point. We can't let's say it's not contradictory to say, well, we need to go toward hydrogen because it's the best long-term solution to go toward climate neutrality, and to tell at the same time that for short-term sustainable aviation, sustainable fuel is the best way, because it's the enabler to significantly decrease the CO2 emissions of the aircraft, and have a very fast infusion within the current fleets, because you have to change probably the fuel system, or adapt it to adapt a little bit the gas turbines for sure, but you can do it with the existing fleet. You don't need to develop a new aircraft, a new product that would take sometimes to infuse within the market. So it's a very good, and that's a must, so as to reach our CO2 targets reduction. There's no point. It's clear. Then, is it the best option? No, because you still have the problems of the NOx. You still have the problem of the contrails, and in addition, so there are several sustainable fuels. There's the biofuel, but you have some problem with the landscape, the space you need, the land you need, so as to make them. So it's not really scalable. And then you have what we call power to liquid or synthetic fuel, which are in any case quite expensive, because so as to produce them, you need first hydrogen, then you need to make carbon capture, and then you need to mix both of them. So the price of synthetic fuel is higher than the price of the hydrogen. So at the longer term, the hydrogen is a better option, but for sure it will require a new aircraft platform, new H2 tanks, new propulsion systems, new H2 infrastructure, and this will take a little bit of time. We target something like 2035 for, let's say, the first phase, but it will take let's say some years, so as to develop all this infrastructure and have it everywhere where it makes sense.
Okay, thanks. Michael, the whole question of short-term versus long-term.
Yeah, so to put it in perspective, if you look at the commercial fleet today, say pre-COVID, was about 30,000 airplanes. The commercial fleet under normal times doubles every 15 years. So 15 years from now, we're talking about a significant number of aircraft. That is the installed base. So sustainable aviation fuels are the next step forward, and that'll preserve the capital asset value associated with that installed base. So it's really important. But as Matthew points out, synthetic or sustainable aviation fuels are not the only solution, right? And even at best, if you're making it from waste streams like sewage or trash, it's still only about 80%, right? There's still a 20% debit there. So we need to continue to improve the efficiency of today's gas turbine engines. The propulsive efficiency that I talked about earlier, going to higher gear ratios as the aircraft installations will permit. Higher thermal efficiency is already being developed. And then hybrid electric. And I want to just say a little bit more about hybrid electric, because some of the members of our panel have talked about some of these smaller vehicles. With about 0.5 megawatt to 1 megawatt, the technology exists today to fly these urban air mobility aircraft. It exists. We're ready to go, right? And there's immediate value for that technology to start to insert it into regional turboprops, where you say a Pratt Whitney PW150 engine on a turboprop is 2,000 shaft horsepower. That's like 2 megawatts. So you can do 50-50 and take advantage of that. And even in a large single aisle, you think about an A320 is 30,000 pounds thrust at sea level. That's about 18 megawatts. That megawatt is 5%, right? And even independent of the weight of the batteries, just designing the gas turbine engine to sit at its sweet spot and handling the transients electrically lets you embrace 3 to 5% efficiency. And that's going to further the technologies. It's also going to enable the certification and the learning that brings more electric into the space, while introducing mass demand for some of those components that some of my colleagues on the panel are depending on for their aircraft.
Neil, I'll come to you in a second. Russ,
Sure.
You wanted to come in on that as well.
Yeah, look, so even if I put on my rosiest of rose-tinted spectacles and think that, every single electric vertical takeoff aircraft is certified as quickly as it possibly can be, that we develop a fantastic hydrogen propulsion system that's mature and certifiable and available at rate. Even with that, most rose-tinted view of what the future sort of 10 years looks like, we are still going to have 20,000 plus conventional aircraft which we are still going to be delivering to satisfy the broader market needs for decades and decades to come. Unless we tackle the fuel type that is being consumed on those aircraft, then the hundreds of millions of tons of hydrocarbons that are being burnt every year from new fossil fuels. Unless we tackle that, we are not going to put a dent in the global impact of aviation on the environment. So absolutely, we need to tackle SAFs. We absolutely need to tackle the further improvements that can be made in engine and airframe technology and concept design. And supporting those things, some of the more disruptive, newer technologies coming in behind them, we'll have an industry to build into. Without some of those big things, we won't have an industry to support.
Okay, Neil, you want to come in on that one as well?
Yeah, I mean, if you look at all these technologies, they're going to evolve. If you look at battery technology evolution in recent times, that's evolving at a rapid rate. If you look at hydrogen development, and again, you have to classify, you can't just say hydrogen. You have to know the difference between green hydrogen, blue hydrogen, brown hydrogen. We all know that green hydrogen is basically cost prohibitive to do in any form of mass scale of transport as it exists today. Can't do it. So you're going to be using a certain form of blue hydrogen. And at that point, it's an offset. It's a case of, whilst it may be net zero at the point of use, you're still going to be having issues. But of course, there is a huge lobby behind this in the oil and gas industry, which is seeing a future for them where they're making commitments to net zero. So they have to go down that development path. So all of these technologies will develop and evolve. But as Michael quite rightly says, this doesn't stop us from doing stuff now. And the reason that we went with a clean sheet design airplane when we first started in this market was the fact that there is, in our opinion, less point in converting existing aircraft and making them worse than they were when they were designed 20, 30 years ago, but actually coming up with a design where the aircraft's been specifically designed for technologies which have yet to fully optimize, which means batteries are heavier, which means the fact that the best power density opportunity we have right now is Jet A fuel. So how do we try and minimize the amount of reliance on the Jet A fuel? How do we lift more of that payload and still do the range and capability that the existing assets can do in order to give you a device that people can support, fund, and understand that this is the way that you move the industry forward? So it's a bit like if you take an apple, you don't really shove the entire apple down your throat in one gulp. You're going to choke to death. You take bite-sized chunks out of it until you've consumed the whole thing. That's no different to this market. But it's being done. You can see those who believe that it can be done with magic pixie dust and be done tomorrow. It's not possible. And you can see those projects that actually have got a long-term view of how we make those incremental steps in order to get to that future. And as panelists have said, there is no guarantee at the moment as to what the end outcome is going to be. There could be a new technology invented. I mean, if anybody had said 18 years ago, been in the meetings with Elon Musk talking about SpaceX, where NASA, Lockheed Martin, Boeing all told him he was completely and utterly barking mad. There's no way that he could do what he could do with rockets. They're now his customers. He is now on a 120 billion market cap company. He was right. We do not know what's coming down the line. But what I do know is that we have some very, very bright people on this planet. We're going to invent some new technologies. We're going to create a new whole sector within aviation. And that's just exciting as hell for everybody.
Well, that would always be a great point to finish at, but we've still got plenty more to talk about. So let's crack on. I'm going to combine two audience questions here. One is a very, very simple one. Does the conventional gas turbine engine have a future? What's the future for gas turbine engines as the aerospace community looks for more efficient propulsion options? And I'm going to combine that with another question, which is really about whether this sort of technology can be retrofitted on existing platforms, or are we really talking about, if there is a breakthrough in propulsion, are we really talking about the engine, the airframe, everything, the way we travel being completely reinvented? Will propulsion be a catalyst for many, many other things happening? Does anyone? Let's go to Michael for that, because you're the company that makes engines at the moment primarily. What's your view on that?
So if you look back all the way back to the Boeing 707, and you look at, say, the Boeing 787, and you compare those two airplanes, they look different? Not really. And yet there's a 70% difference in passenger seat mile fuel burn between those two airplanes. Most of there's a lot of the improvements came from the airframe and from the the materials that were used to make the airframe much lighter. But in concert with that, a predominant amount came from the engine, and engines continue to get better. Between engines and airplanes, about 1.5% per year, year over year, all the way back since the dawn of flight. And so when you look at propulsive efficiency, right, I talked about when we first introduced the geared turbofan, we really sort of dipped our toe in the water in terms of the design space. And we've continued to develop that and work further in concert with NASA, for example. The current generation of engines are bypass ratio of about 12 or 13. We've developed fan systems, installed fan systems with NASA at bypass ratio 18, run them in the wind tunnels. We've developed with the FAA a full engine and demonstrated bypass ratio 15. So we have those technologies ready to go. Similarly in the core, if you look at core efficiency going all the way back to the dawn of the jet age, 82 years ago, the improvements are about 450%. And if you plot that relative to the theoretical rate and cycle limit, we've only come halfway. Now those temperatures get pretty hot, and that's why there are significant investments in both manufacturing, small scale features, as well as new material systems to take advantage of those thermal efficiencies. And then the last piece that I want to touch on is things like electrification. Just as I mentioned, the work we're doing just to take an equivalent, say, of an 1100G that's on the A320neo, and working on essentially in concert with NASA to modify that so it's 5% hybrid electric, even independent of storage, just optimizing, re-optimizing, and re-envisioning how the engine is operated gives you several percent, and that's a stepping stone to a whole new class of technologies that'll open the door.
Okay, Russ, do you want to come in on that? I mean, what does new forms of propulsion mean, and new forms of everything, the way we travel?
I mean, I think Michael's already mentioned that ultimately Pratt already have architectures that could use whether it's hydrogen or SAF or other fuel sources. So no, I absolutely don't think so. There are other technical challenges at an aircraft level in terms of how you store it safely, how you make it efficient for an aircraft to travel the types of missions that we hope them to travel. But no, absolutely not. I think the gas turbine has a long way to go. I think in the very near term, as we've talked about SAF, and I think there's a lot of progress needed there to make that available at price, at volume that's needed. No, absolutely. When we only have one engine that we are the OEM of, which is the Gripen RM12, but we've already used biofuels certified on that engine. So we're doing our piece. Absolutely. My personal view, and Michael, I bow down to your superior knowledge. But I believe that hydrogen combustion in a relatively conventional gas turbine with some changes in material and probably the combustion chamber, absolutely is viable and will happen. It's just a question of when.
Okay, and Matthew, disruptive propulsion, does that change everything for aviation?
Well, it depends what we're targeting. If we're really targeting climate neutrality or climate impact, you will need to change the fuel. There's no other options. Even if you improve your gas turbines efficiency and you're using SAF, etc., you will still have a climate impact which is not neutral. So if you want to do it, another option, you have to go to hydrogen. So then the question is, does it change the propulsion system? First of all, as Ross said, it is changing obviously the aircraft configurations, because you will have to store the hydrogen in let's say liquid hydrogen, and you can store it within the wings. So we will have to find other locations where to put your LH2 tanks, and they are quite big tanks. So either you put them under the wing or above the cabin or at the rear end of the fuselage. I mean, you have to find a place for them, and this will obviously impact the aircraft configuration, change many different things. Now, how to convert hydrogen into thrust? There are two big options. The first one is to use gas turbines. As Michael said, let's say a gas turbine can burn anything. So it can burn obviously hydrogen, but it will change, yes, the combustion chamber, the injectors, also the thermal management system. You will have cryogenic heat exchangers. You won't be able to use the fuel as a muscle. You will have to use other kind of stuff. So there are significant changes within the gas turbines for sure. But yes, you can use it. And the other option, the second pathway, is to use fuel cells. The big advantages of the fuel cells is that it does not produce any NOx, no CO2, no NOx, only water, and it has a quite interesting efficiency, higher, let's say higher than 55 up to 60% of efficiency, so much higher than the gas turbine. But there are some drawbacks. The weight, for example, is a big drawback. But if we couple fuel cells and gas turbine, we may find something which is interesting. We may also, for smaller applications, only use fuel cells. It's another option. So yes, finally, if we start to think about it, the change of fuel can have a significant impact on the propulsion system. And in any case, the thermodynamic cycle of a gas turbine will have to be revisited. The component, the sizing of a component will have to be revisited. So this will be an interesting change. And on top of that, we may see the development of the fuel cells for the propulsion system, which is a huge step for aviation.
Can I pile on to
by all means.
Matthew's point? So let's talk about hydrogen first, burning it, and then I'll end with fuel cells. When you think about hydrogen, it's about 3 times more energy per unit mass than jet fuel. So that's great, but it's about 4 times the volume. And as Matthew said, you have to compress it and store it as a cryogenic liquid. The liquefaction to do that takes about 15 to 20% of the energy that's stored in the fuel. And so you really don't want to throw that away when you get on board the airplane. You want to recover that, especially also from an economic standpoint. It boils off. And so a delayed flight, in fact, even transporting hydrogen around, you may have to do that more than once. So that's a penalty factor from an efficiency, a cost standpoint. So when you take the hydrogen, instead of just burning it, you'd want to use some sort of an expander cycle where you recover that energy on board. Now let's think about some of the other concerns. As was mentioned, oxides of nitrogen, with modifications to the combustor, it is extremely likely, and we believe there are ways to essentially get to equivalent NOx levels when burning hydrogen. The other concern, of course, is water. And if you go through your high school chemistry and you balance the equations, and I went through and did this, it turns out you make about 2.6 times more water when you consume hydrogen on a available energy basis to make the equivalent thrust. And so water, of course, is a greenhouse gas. It doesn't persist in the atmosphere as long as CO2, but contrails, particularly, they reflect sunlight during the day, but they trap the longer wavelength radiation between the ground. And so they do have a fairly significant impact, both in terms of weather patterns as well as radiative index. And the degree to that is not fully understood yet, but there's great breakthroughs being made. Now, I just want to talk a little bit about fuel cells. Fuel cells are really interesting because, and we've worked with fuel cells. In fact, we developed fuel cells as part of the company, and I was actually personally involved. And we put fuel cells on buses, and we were able to run for 25,000 hours in the fleet. So these are PEM fuel cells, proton exchange membranes. But when you think about how they work, a couple things come to mind. Number one is the efficiency is sort of inversely related to the current density, which means that in order to get it to be smaller and less mass, you actually have to decrease the efficiency. And so there's a really narrow ledge there in terms of the trade space. The other thing to think about is the fuel cell. If you're just taking in air at sea level, that's fine. But as you get up to altitude, now you have to compress that air, right? And you probably want to do some recovery on the downside. Well, now that means you have a compressor and a turbine. it's starting to look like, a little bit like the machines we make today. So interesting thought.
It certainly is. Russ, Michael has really touched it there, but I'm going to come to a question from the audience, and maybe you can just expand on this. What does the panel see as the easiest way to store hydrogen? So cryogenic, high pressure, some other chemical method. Could you just talk about some of the challenges involved in storing the hydrogen on board an aircraft?
Yeah, absolutely. I mean, the easiest way to store it is just as a gas. But unfortunately, it takes up such a huge volume that you couldn't possibly build an airframe around it. So typically, you can clearly compress the gas using very heavy, high-pressure cylinders. Unfortunately, that has a compromise of weight. So okay, maybe that's not a great solution. You can actually store it as a solid. So you can use things like hydrides to store it as a solid. That also has some challenges, particularly around the sort of speed of getting the hydrogen on board and release and power density of the release of the hydrides. Or the final option is that you can take it down to sort of minus 253 degrees, which turns it into a cryogenic liquid, which means you can store it in a smaller volume, but you have more complex processes and energy required to go through that process, which in itself needs to be renewable, and also then has all the challenges Michael's already talked about in terms of how do you prevent boil off, how do you ensure that you can deal with the cryogenic liquid safely on an aircraft in a reliable way that's certifiable. Yeah, so there are at least a few different ways in which you can store it. I think our view, and I don't think I've heard any other different views by the other panelists, is cryogenic is the solution which is going to be most efficient for an aircraft, but probably also has with it some of the biggest technical challenges to overcome first.
Okay, I'm going to move on to, we've talked about hydrogen, I'm going to move on to Neil now with electric, and a question from Gavin Armstrong. Electric aircraft have been a focal point of R&D for 20 plus years, but power density is always that limiting factor. What needs to change to make commercial electric aircraft viable at scale in the coming 5 to 10 years? And I'm just going to fire in a supplemental question to you as well from another audience member, really looking at the whole regional space. If electric aviation, hybrid electric becomes viable for short hop flights, is that really going to be more economical than jumping on a train?
Interesting. All of what we can talk about today about hybrid electric flight is, as Michael says, deliverable today. If you look at what we're trying to solve, the reason why we're not flying some of these routes is because of cost of operations. So if we take, just for one example, the fact that we know that with electric motors, we've got the ability to have one moving part. I mean, people focus on fuel burn. What about the oils that are used in an engine? What about the maintenance cycles where you have to rip this engine open every 3,000 hours to do TBO? If you've got an electric motor where your inspection is 30,000 hours, you have a level of reliability. Now, granted, you can't say it's total reliability because for all of the issues you have with a piston stroke turbine engine as failure points, you may say in the grouped electronics that control the electric motor system, you may find gremlins in that. But that said, the actual device itself is being proven at the moment as perfectly usable. The problem is the batteries. We've seen several projects barbecue their airframes because when you try and ramp up the battery technology of today to do the job, it catches fire. That's not good. Now, that technology is going to evolve. Of that, there's no doubt. When you've got people like Elon Musk in this world who are targeting 400 watt hours and targeting new technology that can completely change the game for not just aerospace, but also automotive, that will evolve. Anybody who thinks otherwise is just daft. But how do we power it today? Now, an APU is basically a turbine that is designed to come on at the optimum power and generate electricity and power at that perfect optimum rate. It doesn't have to do the takeoff and landing cycle. It doesn't have to go up and down. It doesn't. So basically your use profile of a generator like that, and that's why we're working with Honeywell and also with Magnix on their electric motors, is to get the demonstration that so long as you've got that reliable fuel burn reduction from just using the APU to power the electric motors. We're primarily using batteries for reserve. We're using it for ground taxiing. We're using the batteries to basically take as much of the emission question out of the flight model as possible without necessarily having to make that the full mission. Now, when it comes to commercial aircraft, as the person asking the question asked, again, it's about volume, it's about weight, it's about power density. There is no way that you can be carrying a ton of batteries per passenger on a commercial jet. It's just on existing technologies. But technologies will change. We're going to be looking at hybrid batteries. We're going to be looking at solid states. We're going to be looking at whole new architectures that are going to appear that will enable us to migrate from the inhibiting problem at the moment of having to use power from the likes of a turbine and go to something that's new. But the electric motor bit won't change because we know that that is very, very good at what it does. It has instantaneous torque, it has reliability, it has high reliability. I mean, all of these things coming together just prove that that is a far better way to propulse the thing through the air. The question is, how do you get the power to that motor to make that viable? Great.
Michael, do you want to come in quickly on this? We're just running out of time, so I just want to get to one more question after this, but come in by all means.
I'll be very quick. So a modern gas turbine engine is 50 to 55% efficient at cruise. A smaller engine like a PT6 or an APU, those tend to be 35% efficient. When you look at going battery to shaft power, that can be as much as 90% efficient. So on the smaller end, you'll see more rapid penetration, and from an economic standpoint, it buys its way in. But as Neil said, that when you start to think of the bigger, right now, the engines are putting out 15% fewer grams of CO2 than the world electric grid.
Great. Well, I think today's discussions prove that, you know, the exciting times ahead, but none of us really know where all this is going. But I'm going to ask everyone, just as a final question, a couple of minutes left, very quickly. Look at your crystal ball, 2035 or even 2040 if you want. What are we going to be flying on? What realistically is air transport going to look like? Matthew, do you want to come in on that? And I'll just ask everyone to be very quick with this one.
Okay, so you will have a mix. You will still have classical aircraft burning SAF, sustainable fuels, potentially assisted with electric motors and batteries. Okay, so as to improve the overall efficiency. So that's for sure. And in parallel of this, you will start to have hydrogen aircraft flying, potentially one of the ZeroE that we'll put on the market near 2035.
Okay, excellent. Michael, what's your vision for 2035?
So it starts with the outside of the engine, and it will have a Pratt Whitney Eagle on the outside. The technologies that are inside, we're ready to bring them forward.
Excellent. Russ?
Yeah, my answer would have been exactly the same as Mathieu. It will be a mix. And I think it'll be a mix in terms of technology, it'll be a mix in terms of platform, and it'll be a mix in terms of the people who are still on the field. And I'm absolutely confident Airbus and Pratt & Whitney will be significant players in that space, and I'm sure there'll be one or two disruptors also that are more present.
So Neil, maybe your aircraft all over the sky. Apart from that, what's 2035?
Yeah, I was just going to agree with the panelists. I mean, I think you have to look at the aerospace industry and look at aircraft across the world in all the different configurations, forms, and way that aircraft fly. Me personally, yeah, I'm hoping we're going to have at least 1,000 aircraft deployed globally by 2040. I have Britten-Norman's commercial aircraft target in my mind of 1,200 aircraft as the most successful British commercial aircraft manufacturer. At 300 aircraft, we're going to be 7th on the all-time list of British commercial aircraft manufacturers. So yeah, we have high ambitions, but we intend to serve a range of markets from regional mobility of people, cargo, firefighting, and of course, non-civilian application as well. So very, very exciting times, but there's going to be all different shapes, different powers, different sources across this whole sector. And that's what makes aerospace such a fascinating industry to be in.
Well, good luck to you, and good luck to all of you with your projects. That just about brings us to the end of our webinar today. Thank you all for your questions, and if we didn't get round to answering your question, I'm very sorry. We had some great questions, and we're very grateful for all your input and engagement. A big thank you to all our panelists and to our sponsor Pratt & Whitney for helping to make today's webinar possible. So Please join us next month when the topic will be the leasing sector and its plans for recovery after a year in which most of its assets have been on the ground rather than in the air. Until then, thank you all for joining us. Goodbye and stay safe.